Hey there! In today's video, we'll dive into some key algorithms that you should know as a software engineer. These algorithms aren't just useful for acing system design interviews. They're also great tools for building real-world systems. We won't be digging into implementation details here. Instead, we'll focus on why these algorithms matter and where we might use them. Understanding the high-level concept is more important than memorizing code for interviews. Now let's see how many of these you already know. First up, consistent hashing. Ever wonder how systems like Cassandra distribute data across multiple servers? They use this algorithm. Picture a ring where each key after hashing maps to a point on it. Servers are assigned ranges on this ring. This means that when adding or removing servers, only keys in the affected ranges need remapping. This is way better than naive hash mappings that will require remapping all keys when servers change. One cool idea here is the use of virtual nodes. It helps to tackle non-uniform data distribution. Check out variants like rendezvous hashing or jump consistent hashing if you want to dig deeper. If you're into distributed caching or databases, consistent hashing is great to know. In the era of big data, ensuring efficient data distribution is critical. Consistent hashing minimizes disruptions as servers come and go. Next, let's talk about Quadtrees for spatial indexing. Quadtrees work by recursively subdividing 2D space into 4 quadrants. Each node represents a region and has 0 to 4 child nodes. Now, why Quadtrees? They enable fast, location-based insertion and searches. We can quickly find points in a radius by traversing the tree and pruning branches outside the range. This makes Quadtrees ideal for indexing spatial data used in mapping apps. Quadtrees are flexible and effective for 2D spatial indexing. Check out other spatial indexing trees like R-trees and KD trees if you want to learn more. Now let's look at the Leaky bucket algorithm for rate limiting. Imagine a bucket with a tiny hole at the bottom. That's our leaky bucket. Requests pour in like water, but if the bucket's full, they are turned away until there's room again. Setting it up is simple. The bucket size controls burst capacity. It leaks at whatever rate we set. Each request is like adding a drop of water. If it's overflowing, requests have to wait. There's other rate-limiting algorithms, like token bucket and sliding window counter. They are simple and effective algorithms, with each making trade-offs between accuracy and performance. Next up, tries, a tree structure optimized for storing strings and prefixes. Each node represents a common prefix, with nodes sharing prefixes using the same subtree. The real power of tries lies in fast lookup speed. Searches are super efficient. Imagine searching for a word or a prefix in a large dataset. With tries, we don't need to sift through every entry. Instead, the search elegantly progresses through the tree, moving character by character, following branches that match the search term. This makes operations like autocomplete in search engines or text editors lightning fast. Way faster than with structures like hash tables or arrays. One catch. They can be a bit greedy with memory. This is because each node often maintains multiple child pointers. There are variants like Radix trees or Suffix tries that optimize memory usage. Tries are a powerful foundation for scalable string-based searches. Next, we have Bloom filters. These are probabilistic data structure for set membership checks. Picture a bit array combined with some hash functions. Items get hashed and their corresponding bits set. To check membership, we see if all the bits are set. If not all set, definitely not in the set. If it's all set, maybe in the set, but watch out for false positives. We can remove elements once added, And what about those false positives? We can tweak things like size or hash functions to balance space and accuracy. Bloom filter shines in caching, deduplication, and analytics by quickly filtering out noise. Last but not least, let's talk about consensus algorithms. In distributed systems, reaching consensus, that is, ensuring all nodes consistently agree on a shared state, is tricky, especially with network issues and failures. Algorithms like Paxos and Raft are designed to address this challenge. Now let's focus on Raft since it shines through its simplicity and efficiency. Raft elects a leader to manage state replication across the cluster. If nodes fail, Raft ensures the system stays operational to prevent inconsistent data and downtime. A major plus is that it's easy to understand and implement. Many distributed systems like Kafka and etcd have adopted Raft for replication, failover, and leader election. Paxos predates Raft and is historically significant but more complex. And there you have it, a quick tour of the whys behind some essential algorithms. What other real-world applications have you seen or used these algorithms in? Drop a comment below. Let us know if you have any other algorithms you find useful as an engineer. If you like our videos, you might like our system design newsletter as well. It covers topics and trends in large-scale system design, trusted by 500,000 readers. Subscribe at blog.bytego.com.